Alright, so if you've ever used a computer, you've probably also used a zip file or some sort of compressed file format, right? So have you ever thought about how that works? It's kind of a weird way to introduce this video, but basically I wanted to make some sort of file compression, I don't know if I can call it software, but just an app that does it. And I was kind of looking into the zip file format and file compression in general, and the variant that I made of zip is not as good as zip. So a couple things it doesn't include is it doesn't have its own file header, which is kind of a very massive thing because the file header includes a lot of information. If you start reading up on these, you can see everything that's in here. My version basically takes in some file, typically a text file, but you could probably also just read any file as long as, actually, yeah, you can read any file and then convert it into binary and then read it back. But I just do text files for now. So it takes in a file, it converts it into a binary compressed version and makes a key, and then using that key you can get back the file. So let me show you how it works real quick. So here is us basically compressing the Declaration of Independence, right? So here's the Declaration of Independence. There you are. All right, so only 59 lines of text, and we're going to compress it and see how the file size has changed. So notice how you run the program is you have cargo run, and then I guess you need these two hyphens for Rust for it to recognize that you want to pass an argument in here. And then, so I have E for encode, and then example text, so the text that you want to encode, the key that you want to make after that. So the key is basically going to map all the characters in this text to some binary representation, and then the out file, which is the actual binary file that you're compressing to. It's pretty fast. This is only 59 lines of text, so it's really not that big of a corpus or anything. So yeah, we have an old file size of around 10,045 bytes and new file size of almost 7,000 bytes. So it does compress it. It's not as good as zip, but the idea is I just wanted to learn how it works, and hopefully for you watching the video you can get an idea of how you can make your own zip-like file compression system. And so yeah, so what does it actually generate? So it generates a key file, which again, it's basically how all the characters line up with some sort of representation. Keep in mind that the new line character is really annoying, and there's better ways of dealing with it than what I've implemented. So I will tell you how you can deal with it better, but I'll tell you what I did first. So every new line is just mapped to an underscore right now. The reason why the new line is annoying is because if you try to read it, even character by character, well, for one thing, string processing in any language other than the Python or JavaScript maybe is really annoying. But in Rust, how it works is that when you read a file, you can read it string by string. You could probably also read it character by character. And I'm just reading the file string by string, or line by line, I should say. And of course, a new line character breaks lines, right? So that's why it causes this program to break, as if you have a new line character. So I just mapped it to the underscore. I mean, you can also map it to anything you want. Or even better, what you should really do is either read the file character by character so it doesn't make a difference, or make some sort of other object to represent characters, like a wrapper around, for instance, n, so it's not just a character type, basically. Because when I'm using a character type, if you try to use something like %sign to represent a new line character, well, if you get an actual %sign in the text, that's going to screw everything up. So keep that in mind. But yeah, so we can run a diff on our well, not yet, because we haven't actually converted it back. But yeah, so here's the binary version. So it's around 18 lines of pretty long binary. Keep in mind that what we're trying to do here, right, is each character in Rust, I think, is like a byte, maybe 4 bytes. I guess I could look it up. Yeah, so it appears that the size of a character in Rust is 4 bytes, and each byte is 8 bits, right? So if we can convert a character representation to anything less than 4 bytes, which is 32 bits, then we're going to be saving data. So for instance, a space, which would have been 32 bits, is now only 4 bits, right? An exclamation point is only however many bits. So that's the idea of behind compression, is that you take some sort of representation, you make it smaller. Okay, and so now let's actually decode the file. So I actually kind of forget the format for decoding, so if I would just run that, it's going to give you a little help text. And it's saying a warning because I guess the naming convention in Rust is that you want snake case, some sort of identifier, I guess maybe a crate or something. I'm not entirely sure. Anyhow, so we have an input file .binary, so that's going to be our out file that we just made. Then we have a key file name, which is the one that we just made, and then I'm just going to say deck.text. That's going to be the decoded. All right, and now if you run a diff between the declaration of independence we just decoded and the example text, you're going to get no new line at the end of the file. That's just because of the way that this is encoded. Sometimes it will remove a new line. So a couple of problems with this implementation. For one thing, the biggest thing is that the new line character is going to cause a problem. And I think you can tell by what we just said. We've just mapped new line characters to underscores. Another problem, actually that's probably the biggest problem, is just that the new line character is going to cause issues. We can try another encoding of a bigger piece of text. So we're going to encode War and Peace. That might take a moment. So War and Peace is this guy. Yeah, it's pretty long. So yeah, this project is not meant to be perfect. It's just meant to kind of work and just show the idea behind file encryption and decryption. So now we're going to, yeah, so you basically lost, like almost 100,000, how many is this? It's kind of hard for me to see, like 1 million bytes or something. So that's pretty sizable. And then we're going to decode it. And then I'm just going to go over how this program actually works. All right, so we decoded it. It took a little bit of time, and I guess I just kept it as declaration of independence. And now we have basically all of this text. Yeah, so really long. It does work. It's just not, obviously it's not optimal. So how does this work? So basically I followed this Huffman Encoding page on Wikipedia. Funny story, so I guess this guy was a student at MIT, and he was assigned this term paper to find an efficient way of sorting by frequency or rather a code, an efficient way of encoding information. And he uses this frequency sorted binary tree, and it was actually the most efficient method. But the idea is that you take in all this text and you read it character by character, and you assign a frequency to each character, right? So E might be frequency of 4, and then N might be frequency of 2. And then from there, you assign, based on if you're going left or right, a 0 or a 1, and that's going to be the binary string. So I think in this example they did, if you're going left, it's 0. It really doesn't make a difference if it's 0 or 1. It just has to be one or the other. So for instance, E might be 0, because you're going left once, 0, 0, right? And then A might be 0, 1, 0. And then something like this, let's do maybe P would be 1, 0, 0, 1, 1, right? So I mean, you can tell it's 1, 0, 0, 1, 1. So that's one way of making the Huffman tree. And then they have this nice diagram of explaining how it actually works. So you go through all the nodes, and in this case I think they go by the least frequent here. So it seems that there's 5 and 6. Those get paired up and become D. And then the next step, you do the same thing. It's basically recursive, so you just find the 2 lowest nodes, pair them up. So now it's no longer 6 and 5, it's going to be 6 and 7, pair them up. And then you go to the next one. So what's the 2 lowest nodes? It's going to be 11 and 13, pair them up. And then you pair up 15 and 24 to get 39. And yeah, that's not the same example that they had here before, but that's okay. And so, yeah, so we basically do the same exact thing. So going through the code, I'm only going to really do the encoding part because the decoding is just an opposite of it. So you read in some content from the string, so the file itself, and then you're going to make a hash map of the tree. So get hash of tree, that's going to be in, I guess, Huffman, that class. So get hash of tree. And that's going to create basically a tree of option boxes, and the reason why you do that is because I wanted to get like pointers to each node, but you can't really do that in Rust, it seems. So the best thing I could do was an option box. And then you make a hash map of each of the nodes and put them in here, and then just keep on traversing the nodes. So in general, how you should read this file is that you get a text, right? You read the whole string, and then you're going to get a hash map character frequency of this, right? So that's going to be basically doing the first step in the Wikipedia article, which is assigning each character a frequency. Then from this hash map, you're going to use that to basically assign each of the characters that was in this Wikipedia article into another hash map, or rather a wrapped hash map. So it's going to be a class that I call like my B tree or something. It's a binary tree. And you're going to completely follow these steps. So you're just going to sort the last two nodes until there's only one node left, or rather combine the last two nodes until there's only one node left. And when there's only one node left, you're basically done. And then you're going to assign numbers to each of the nodes. So that's how I did it. And yeah, hopefully this gives you a little bit of intuition on how file compression is done. Again, this isn't perfect, but I thought it was a little interesting project for Rust. So yeah.